Hello students, welcome to lecture 9 of atomic structure. Our topic is quantum mechanical consideration of subatomic particles. Two important developments are there in quantum mechanics. Number 1, dual behavior of matter. And number 2, Heisenberg uncertainty principle. Let us discuss the first one, dual behavior of matter. De Broglie in 1924, De Broglie in 1924 proposed that matter exhibit dual behavior. That means it has particle nature and wave nature. So that matter has dual nature, particle nature and wave nature. Like electron has particle and wave nature. And de Broglie gave a formula for wavelength and momentum. Lambda is equal to h by mv. M means particle mass, lambda is the wavelength, and h is the Planck's constant, and m is the particle mass, and v is the particle velocity. So mass into velocity is equal to momentum. So we can write here h by p. So lambda is equal to h by p. So this is the de Broglie formula. Next, second one, Eisenberg uncertainty principle. In 1927, Werner Heisenberg stated that it is impossible to determine the exact position and exact momentum of electron simultaneously. In 1927, Werner Heisenberg stated that it is impossible to determine the exact position and exact momentum of electron simultaneously. Means at a time we cannot determine the exact position and exact moment of electron. That means if the position of electron is known with accuracy, the position of electron is known with accuracy, then velocity of electron will be uncertain. Velocity will be uncertain, means large. And if the velocity of electron is known with accuracy, the velocity is known with accuracy, then the position of electron will be uncertain. the position of electron will be uncertain. And Eisenberg gave a formula delta x into delta px greater than or equal to h by 4 pi. So here delta x into p is the momentum, means mass into velocity, delta mvx mass into velocity greater than or equal to h by 4 pi, or delta x into delta v x greater than or equal to m will come here, so h by 4 pi m. So here the delta x is a uncertainty in position of particle, and delta px is a uncertainty in momentum of a particle. And m is the mass of particle, and v is the velocity of a particle. So this is about Heisenberg uncertainty principle. In 1927, Werner Heisenberg stated that it is impossible to determine the exact position and exact momentum of an electron simultaneously. Next one, significance of uncertainty principle. The Eisenberg uncertainty principle is only for motion of microscopic objects and is negligible for macroscopic objects. So this Eisenberg uncertainty principle is only for motion of microscopic objects. And it is negligible for macroscopic objects. Let me take examples. Example, the mass of macroscopic object is is 10 to the power of minus 6 kgs. According to Eisenberg principle, delta V into delta X is equal to H by 4 pi m is equal to, H is the Planck's constant, 6.626 into 10 to the power of minus 34 joule into second divided by 4 into the pi value 3.14 into m. The mass is 10 to the power of minus 6 kgs. Is equal to if you do this calculation, we will get 10 to the power of minus 28 meters square per second. So this value is very small. It is too small. So the value is insignificant. So the value is insignificant because it is a very small value. And for example, the mass of microscopic object is mass of microscopic mass. For example, I am taking electron. Electron is a microscopic particle. So the electron mass is 9.11 into 10 to the power of minus 31 kg. So according to Eisenberg uncertainty principle, delta V into delta X is equal to H by 4 pi m is equal to the H value, Planck's constant 6.626 into 10 to the power of minus 34 joule into second divided by 4 into pi value 3.14 into mass of that electron is 9.11 into 10 to the power of minus 31 kg is equal to, if you do this calculation, we will get 10 to the power of minus 4 meters square per second. So here this value is a significant value. The value is significant value. So for macroscopic objects, the value is insignificant. For that microscopic objects, the value is significant. So the Eisenberg uncertainty principle is only for the motion of microscopic objects or microscopic particles. It is negligible for macroscopic objects. Next, let us solve some problems from our textbook. The problem number 1.10. What are the frequency and wavelength of a photon emitted during a transition from n is equal to 5 state to n is equal to 2 state in the hydrogen atom? In previous lecture, we discussed about line spectrum of hydrogen. So here we have a problem which is related to line spectrum of hydrogen. So here the photon comes from 5th state to 2nd state. Means here the 5th state is the initial state and 2nd state is a final state. Let me take here 5th state and final state. So here n is equal to 2 and here n is equal to 5. So the photon comes from 5th to 2nd. So this is the initial state and this is the final state. So Ni initial state 5 and Nf the final state 2. And we know that delta E is equal to h nu. So here we have to find out the frequency and wavelength of a photon. The frequency. So we have to find out that mu. Mu is equal to delta E by H. Delta E by H. And we know that delta E is equal to we have that formula 2.18 into 10 to the power of minus 18 joules into 1 by Ni square minus 1 by Nf square. So here delta E is equal to 2.18 into 10 to the power of minus 18 into 1 by Ni square. Ni initial is the 5, so 5 square minus 1 by Nf, final is the second state, so 1 by 2 square, and is equal to 2.18 into 10 to the power of minus 18 into 1 by 25 minus 1 by 4 is equal to 2.18 into 10 to the power of minus 18. If you do the LCM, we will get 25 into 4, 25 cancel 1 into 4 4 minus 4 cancel 25 into 1 25 is equal to 2.18 into 10 to the power of minus 18 into 4 minus 25 21 minus 21 divided by 100 is equal to, if you do this calculation, we will get 2.18 into 10 to the power of minus 18 into minus 0.21 is equal to, if you do this calculation, so here I am taking 2.18 into 10 to the power of minus 19, and here I am taking minus 2.1. So here, instead of 10 to the power of minus 18, I am taking 10 to the power of minus 19. So here we have to take 2.1, so minus 2.1, so is equal to, if you do this calculation, we will get minus 4.58 into 10 to the power of minus 19 joules. So this is delta E. So here negative will shows the emission energy. Already we discussed that N initial is greater than N final. If N initial is greater than N final, then the delta E will be negative. So here the delta E will be negative. So here frequency mu is equal to delta E is this one, 4.58 into 10 to the power of minus 19 divided by, and H Planck's constant 6.626 into 10 to the power of minus 34 joule into second, and here joule. So if you do this calculation, we will get mu is equal to 6.91 into 10 to the power of 14 per second or hertz. So this is the frequency. So here this negative will shows the emission energy. So here the photon comes from fifth level to second level. When the particle comes from higher energy level to lower energy level, then the energy will be emitted. So here the energy emitted, and here the spectral line is in the visible region, and it is a Balmer series because the photon comes from higher level to lower level of second. So if the particle comes from higher level to lower second level, then the series is called Balmer series. So it is a Balmer series. Already we discussed in previous class. Let me go back to see that series. So these are the series: Lemon, Balmer, Passion, Broglie, and Fund. If the electron or particle comes from higher level to lower second level, then the series is called Balmer series. So here the photon comes from higher level to lower second level, then this series is called Balmer series, and this series appear in the visible region, and this is the frequency. Then let us find that wavelength. Lambda is equal to c by mu. So c is velocity, 3.0 into 10 to the power of 8 meter per second, and divided by 6 point, mu is this one, 6.91 into 10 to the power of 14 hertz. If you do this calculation, we will get 434 nanometers. So the wavelength lambda is equal to 434 nanometers. So the frequency is 6.91 into 10 to the power of 14 hertz, and the wavelength is 434 nanometers. Next one from our textbook, the problem number 1.12. What will be the wavelength of a ball of mass is 0.1 kg moving with a velocity of 10 meter per second? So here mass and velocity given. So m is equal to 0.1 kg and velocity v is equal to 10 meter per second. So we have to find out that wavelength. So according to de Broglie, lambda is equal to h by mv is equal to, h is the Planck's constant, 6.626 into 10 to the power of minus 34 joule into second, divided by m, mass is 0.1 kg, into velocity v is the 10 meter per second. So if you do this calculation, you will get lambda is equal to 6.626 into 10 to the power of minus 34 meters, because here 0.1 and here 10, so these two will be cancelled. So remaining value is this one, 6.626 into 10 to the power of minus 34 meters. Next to problem number 1.15. A microscope using photons is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? So here, Eisenberg uncertainty principle, delta x into delta p is equal to h by 4 pi, or we can write that delta x into p is the momentum, means mass into velocity. So here m delta v is equal to h by 4 pi. So here we have to find out that uncertainty in velocity. So delta v is equal to h by 4 pi into delta x and m. Delta x into m is equal to h is the Planck's constant. The value is 6.626 into 10 to the power of minus 34 joule into second, divided by 4 into the pi value 3.16 into delta x. So here the distance is 0.1 angstroms. So we have to convert into meters. So 0.1 into 10 to the power of minus 10 meters. 1 angstrom is equal to 10 to the power of minus 10 meters into, and mass of photon 9.11 into 10 to the power of minus 31 kgs, and is equal to, if you do this calculation, we will get 5.79 into 10 to the power of 6 meters per second. So this is the uncertainty in velocity. The uncertainty in velocity is 5.79 into 10 to the power of 6 meter per second. So here the photon is a very small particle. So that small particle uncertainty velocity is 5.79 into 10 to the power of 6 meter per second. So it is a significant value. And we know that Heisenberg uncertainty principle is applicable for only microscopic particles. So here the photon is a microscopic particle, and the uncertainty in velocity is 5.79 into 10 to the power of 6 meter per second. So it is a significant value.